Okay, so a good way to start this is by drawing a diagram. So we've got a lower pipe down here with a cross-sectional area given by 3 centimeters squared and with a speed for the lower pipe of 7.20 meters per second. And then it goes up a hill into an upper pipe, and the cross-sectional area of the upper pipe is equal to 6.20 centimeters squared, and the height difference between these two, h, is equal to 10.0 meters. And then part A of the question asks us for what's the speed up here in the upper pipe. So for that one, we can use the constant volume flow rate equation. So we know that the cross-sectional area in the lower times the speed in the lower is equal to the cross-sectional area of the upper times the speed of the upper. So we want the speed in the upper pipe, which is equal to AL VL over AU. And so now substituting in, we've got 3.00 centimeters squared times 7.20 meters per second over 6.20 centimeters squared. The centimeters squared is cancelled out, and solving that on the calculator, we end up with 3.48 meters per second. And so that's the speed in the upper pipe here. So VU is equal to 3.48 meters per second. And now part B tells us that the pressure in the upper pipe, so pressure upper, is equal to 1.8 times 10 to the 5 pascals. And we're asked, well, what's the pressure in the lower pipe? So in order to do that, we're going to need to make use of Bernoulli's equation, which tells us that the pressure in the lower pipe plus a half rho V lower squared plus rho G H lower is equal to P upper plus a half rho V upper squared plus rho G H upper. Now notice that rho, that's the density of the water, so that's not dependent on which pipe we're in, nor is G the acceleration due to gravity. So what we're trying to find is this P lower. So let's make that the subject on this left-hand side. So we've got PL is equal to PU plus a half rho VU squared minus VL squared plus rho G, and then we've got H upper minus H lower. And the difference between the upper height and the lower height, the upper height is 10 meters higher than the lower height. So that's equal to this thing here. That's 10 meters, that difference there. So now what we can do is we can substitute everything in. We need to substitute everything in SI units. So the pressure in the upper pipe is 1.8 times 10 to the 5 pascals. So if that was in atmospheres, we would need to convert it. Plus a half times, now the density of water in SI units is 1,000 kilograms per meter squared, per meter cubed, sorry. Now V upper, that's equal to 3.48 squared, we just calculated that. And V lower, that's equal to 7.20 squared plus rho 1,000 times G, which is 9.8, times, we said the difference in these two things was the 10 meters. So now what we can do is solve that on the calculator, and we end up with 2.58 times 10 to the 5 pascals. So that's how we solve that problem.